Consider the lowly conductor. A conductor is just a material in which electrons can move freely. And so typically it's a metal. Metals have valence electrons, which are loosely bound to the nuclei, so they can move in response to an electric field. And an electric field is induced in a conductor in this direction. It means electrons would move in that direction. They would experience a force opposite the electric field. Remember, electric field is the direction positive charges move. So, one thing about conductors, there's a quality that we're interested in, which is how easy it is for the electrons to move in there. And there's a measure of kind of how hard it is for the electrons to move, which is called resistance. Resistance. It's sort of a sense of how hard it is for electrons to move through, for charge to move through. We're going to talk in the future about current, which is the flow of electrons. And so the current is going to be basically inversely, for a given electric field, inversely proportional to the resistance. There's a thing called conductance that we're not going to really address, but resistance is how hard it is. It's something where the electrons have a lot of difficulty getting through. It's going to have a high resistance. As an example, here is a thing called a resistor. It has a known resistance, a known difficulty for charge to flow through. And knowing that value, knowing exactly how much resistance there is, it ends up being a really useful thing. Resistance is measured in ohms. R is the symbol. It's measured in ohms, named after Georg Ohm. So what we want to see is what goes into that. Okay, why does it happen? What makes things, resistors, have less resistance or more resistance? Or I should say conductors have more or less resistance. Well, one thing is the nature of the material. Okay, if we think of this as like this is a lattice structure of the metal, of the atoms in the metal, and if I send a charge through there, and you can think of the electric field as being how steep this is. If it's a very small electric field, that electron doesn't move very aggressively through there. And you can think of this as interactions with atoms. Look, it's not collisions necessarily, but as it approaches, as a free electron approaches each atom, it's going to have an interaction with it. There's going to be forces involved with it. Okay. So you can see this is bouncing around kind of randomly, and that's really what's happening with electrons in conductors. They're bouncing around kind of randomly, interacting with atoms along the way. Each interaction you can think of as removing a little bit of energy. So you could see if these are more densely packed, if these nails were more densely packed, there'd be more interactions, more energy lost, transferred into heating. And that's really what's happening in conductors. If there's a lot of resistance, there ends up being a lot of heating involved because there's energy transferred into heating. So honestly, if you want to use a conductor, not a resistor, but a conductor that has low resistance, that would mean there'd be very little energy lost. And that's a good thing for most applications. Now look at the width here. You can see if I had a whole lot of balls go in here, some of them would be bouncing off there, and if this were bounded on the sides, it'd be bouncing, losing energy every time it hits the sides. So really what we want is a really, really wide path in our conductor. Think of water through a hose. Okay? If this is the hose, some water can flow through at a certain rate. But if this is the hose, more water can pass through. So you want more area. And you see this area here, they call that the cross-sectional area. The area of that circle would be the cross-sectional area. So all things being equal, We want a material that doesn't have as many of these interactions. We want a tube, I want to say a path, that has a big cross-sectional area so it doesn't bounce up against the edges so much. And we honestly don't want it to be too long. The longer it is, the more it has these interactions with this thing. So we don't want it to be too long. So this resistance actually ends up being logically proportional to how long I'm not going to call it a tube because it's really a solid piece of metal, how long that piece of metal is. It's going to be inversely proportional to the area, what they call the cross-sectional area. So this is length, L. This is the cross-sectional area. I'm going to write it as cross-section area, just to save myself writing. And that is the area of this end piece here. I drew it kind of like it's cut away, but if we look at that, the circle there, that's the cross-sectional area. Bigger that is, the less interaction with the edges. Okay? And there's going to be this other thing here. That's a rho. And rho is the resistivity. And the resistivity is the characteristic of the material that gives it resistance. Okay, so if I have a chunk of metal, a chunk of, let's just say, iron, it's going to have a certain resistivity. Okay, and that's a characteristic. The resistivity, by the way, would be in ohms meters. Because if I do meters squared divided by meters, so it's ohm meters. Let me write that up there. Ohm meters. Sometimes you'll see it written, okay, like that. So that's resistivity. That's the nature of the material. That's how resistive the material is. So if I have a chunk of iron, I can increase the resistivity. This is a given. This is a number. I can increase the resistivity by making it longer or by making the cross-sectional area smaller. Similarly, if I make the cross-sectional area big and I make it short, there's not going to be as much resistance, even though iron has this characteristic resistivity. So that's how we calculate the resistance, based on these factors. Now, let me say also, this does not have to be a circular piece of metal. It can be any kind of piece of metal. You could have a rectangular piece like this. And if we're talking about the current, the charge is running through in that direction, that would be the cross-sectional area, and this would be the length. You could have something, I don't know why you would, but you could have something like a dime or something like that. And again, it really matters what direction you're trying to send the charge. The resistance between here and the other side of that dime would be how hard it is to push charge through there. This would be the cross-sectional area, and the length would be this tiny dimension. So resistance can be calculated if you have all these things. Alternatively, we could figure out what the resistivity of a material is by taking a test chunk, finding the resistance, which I'm going to show you how to measure in the next unit, in the next video, and determining the dimensions.